No. Okay. So what day week is it? On Monday, we had, let's back up a page. Just started talking about, we are very short on students today. You normally have some? My goodness. We had just started talking about the different biomolecules. And so we had just introduced carbohydrates. So remember, as we're going through this, you really want to focus on what is the point of this particular biomolecule for the cell or the tissue or the body, and what is at least one feature of this biomolecule that will allow you to tell this biomolecule apart from the other biomolecules that we're going to talk about. Can I say the word biomolecule a few more times? So we had just started talking about carbohydrates. And this is a very familiar molecule, okay? Personal favorite of mine. Okay? And so I had said, let's picture the donut. Okay? Glazed in sugars, which is a carbohydrate, and then the body of the donut itself. Okay, glutinous, delicious, and also a carb. Okay, so the perfect example of a carbohydrate. And so when we think of carbohydrates, largely we tend to think of fuel. This is particularly true when we're picturing, excuse me, our simpler sugars. Remember, when we think of simple sugars, we really mean just monomers. And then when we start to think of complex sugars, right, our polymers, these can be some of our building materials. So we can think of things like cellulose, right, the compound that holds plant material, like our grasses, upright. And we'll look at a little bit of both of these as we go through our carbohydrate unit. So let's take a peek at what makes a carb a carb. Okay, so we're going to focus first on monosaccharides, because being simple sugars, it's a little easier to pick them apart. So remember, when I say monosaccharide, okay, mono just means one. Remember, we learned how to count on Monday. And saccharide just means sugar. Okay, we can actually see the word saccharin written on some sugar packets. Okay, so it's the same word. All right, so the first feature that we're going to look at is what's called a hydroxyl group. We're actually familiar with hydroxyl groups already. That's this little bad boy over here. And we've talked about him already, right? Remember, this is the group that we used in order to make and break up Carl and Jane when we were doing our hydrolysis and dehydration synthesis. Okay, so we've already looked at these OH groups in pretty close detail, so now we're just going to name them hydroxyl. Okay. Now, hydroxyl groups, on top of being really important for hydrolysis and dehydration synthesis purposes, are generally really important groups. Okay? And that's because, as we'll find, the oxygen compound found in this group creates an interesting relationship, which we call polar. Right? So having an oxygen in this group is an interesting relationship. It's kind of like having a selfish roommate. And we've all had this selfish roommate. Okay, you trade off buying toilet paper, that's fine, except you know that your roommate uses way more rolls. Okay? You split the grocery bill, even though you know that your roommate eats way more than you do. Way more. My husband is absolutely like this. It drives me insane. Okay? He uses way more toilet paper. Way more. Okay? So, this selfish roommate. Okay, we've all had one. Okay, not enough that you throw them out, but definitely enough that you like complain about them when you go out, right? Okay, oxygen is the selfish roommate. Okay, it's selfish with electrons. Okay, so we're not positive or negative. Okay, this is a neutral group, but it's still selfish. Okay, so this is a little selfish, a little bit negative, right? They share the electrons, but it uses them way more, right? And so our hydrogen ends up a little bit positive. A little bit positive, it doesn't think it'll live with it next semester, right? Okay. So because our oxygen is a little bit negative and our hydrogen is a little bit positive, it has an interesting relationship. Okay, it temporarily bonds with things, particularly other things that have hydrogens and oxygens in them, like water, which also have selfish roommates. Okay, and we know this intuitively. Okay, if you take a spoonful of sugar and dump it into water, what happens? It dissolves, right? So we know that sugars bond or play well with water. Okay, we call that hydro for water and philic. It's water loving. And that's due to this polarity, okay? This relationship that oxygen has set up by being the selfish roommate. Okay, so anytime that you see any compound that has a lot of oxygen, we're going to have this happen. Okay, and our sugars, our carbohydrates, have a lot of oxygen because we have these hydroxyl groups. So let's look at our example monosaccharides on the right hand of the screen. If I give you structures that look like this, okay, just by taking a step back and glancing at them, the very first thing we see is hydroxyl, 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 right? They make up an enormous proportion of our structures. Bam, 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 bam. Okay, that's 5 on one structure. That's a ton. Okay, same thing with our ring version. Boom. Okay, predominantly hydroxyl groups. Okay, so we know that these over here, even if I didn't already know that they were carbohydrates, are going to be polar, they're going to be hydrophilic, and this is going to lead us to think this is a carb. Okay? So the first thing I would do on a test is circle them and say, oh, carb, or hydroxyl, 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 hydroxyl. Okay, I think I know what's going on here. Okay, with me so far? Yeah.
Is that going to be the main way to tell carbohydrates and lipids apart? So I'm looking at that chain structure, and it really reminds me of lipids. I'm worried about confusing the two.
So we will be able to compare these to lipids, and so I would say yes. So when you have a lipid, as we'll find, these hydroxyl groups are going to be entirely absent. Okay. And so this is a really good key feature. But you're right that a lipid does still have the chain part, but it's not going to have those hydroxyl groups. Okay. So they're a really good key identifying feature. Good question. Okay. Now, if you happen to have the chain, one other feature that you can use, let's change colors, is what's called the carbonyl group. Okay, for the carbon. Okay, so that's what we have over here. So the carbon double bonded to the oxygen with a little hydrogen sticking out. Okay, you're going to see this R business a lot, both in biology and if you take chemistry as well. Okay, R is the lazy man's way of saying something else, and there's other stuff. Okay, an infinite number of other things. Okay, so here's our example. If I look at my chain version, here's my carbon, here's my double bonded oxygen, here's my hydrogen, there's my other stuff, right? Can be very, very long, can be very, very short. I don't care because this part is the part that makes up the carbonyl group, right? On the chain structure, the carbonyl group is very easy to see, right? That double bonded oxygen sticks out like a hiker's thumb. When I get a ring structure, you really can't see it. Okay, it's there. Here's my O with 2 bonds and the rest of it. Okay, it's kind of like hidden in and folded in on itself. And so it's a lot harder to find that, and that's okay. And this is why you have more than one way to recognize things as a carbohydrate. Now this happens because carbohydrates change form when you stick them in water. Okay, and that's what this last sentence means. Aqueous means in water, if you've not heard that word before. Can that make sense to us, right? We have sugar cubes or sugar granules in our hand, but when you dump them in water, they dissolve. Okay, we know they're still there. You can taste it in the water. Might even make the water viscous if you've added enough sugar. We can't see the sugar cubes anymore, right? They've changed form. Okay, so that's all we're seeing here. We're just seeing it in the molecular drawn form. Okay, so we're changing the shape of the sugar. It's still sugar. We're just folding it up. Okay, so if I were to pick how to do pick a carb, I'd use the hydroxyl first, because the hydroxyl is very obvious no matter what form I'm using. And then I'd use my carbonyl as a backup, right, because it's less obvious if I'm glancing at a structure. Okay, but a carb is always going to have a bunch of hydroxyls. And those are much easier to pick out no matter what I'm looking at, right? Okay, any questions about what we've got going on? Got quite a busy slide now. Okay, any questions online? Okay. So let's take a look at a more complex sugar. Okay, so what if I have 2 monosaccharides and I want to make a disaccharide? Okay, so you guys have actually done this already, right? We did this on Monday. And now we're just going to use our terms when we do it. So here's Jane again. Good old Jane and Carl. Right? These are monomers, and now formally monosaccharides. Okay? Now they have their independent hands sticking down, which we know are hydroxyls. So we can name those. Okay, and remember, we have to use hydroxyls if we're going to make our monosaccharides a disaccharide. Remember, mono means 1, di means 2. Okay. If I have 2 monosaccharides and I'm going to make a disaccharide, am I going to use hydrolysis or dehydration synthesis? I'm going to make a disaccharide. Dehydration synthesis. Good. Okay, I am spelling that right. fit. Smush that in next to Jane there. Okay, remember, here's the way we're going to remember that. Either remember it because we're going to dehydrate out some water. Okay. Or you can remember it because we're going to make something big. Or you can remember it because dehydration synthesis has two words, and I'm starting with two compounds. Okay, so you've got lots of tools in your toolbox to help remember these things. Okay, so let's practice our dehydration synthesis with Jane and Carl. Okay, so here are my two hydroxyl groups. Okay, remember I have to get rid of water. So I need to get rid of one oxygen and two hydrogens. There it is. There's my water. Bye-bye. Okay, so that has now left poor Jane with her bloody stump. Okay, remember, nobody can have a bloody stump, so that's a problem we've got to solve. Carl here has one oxygen left, right? He's got himself a nice fist. So when we're done then, Carl's going to take his fist and use it to hold Jane's bloody stump. It's fine. Okay, so that's where they're connected, right? One oxygen. Nice, holding hands, swinging hands together. Is that a question?
Yeah.
Okay.
Does the CH2OH have a charge on just negative one or positive one? If those send out the hydrogen in that one, like if they can share the oxygen.
Say again.
How do they share that oxygen between two different bonds? Like atomically then, I guess is the question. So if they're covalently bonded at that junction,
Yep.
is the CH2OH have the same property as hydrogen, where is it contributing one to the oxygen?
Yeah, so remember our carbon just has 4 bonds that it can do. And so we still have 4 bonds here.
Okay.
Oops, not that one. Not that one. We got excited. Carbon got very excited there. 4. There we go. So carbon to oxygen bond is a pretty standard bond. Yeah, the particular shape of that bond is doing kind of something funny, but a carbon to oxygen bond is a shine. In fact, we are going to talk about covalent bonds in a second, but very light-handed. Okay, so don't worry if you didn't get all that. We're going to talk about that in 2 shakes of a lamb's tail. Does the rest of this make sense? Is it still good? Okay, so leading into her question then, in a very light-handed way, is that dehydration synthesis is making covalent bonds. Okay, which remember has a lot to do with electron sharing. We're not going to get very deep into any of this. That's a lot of chemistry stuff, which is not our problem. Okay, but the one thing I do want to remind you, which we just sort of talked about, is what are the elements that are in this bond here? Okay, so oxygen is bonded to what? What did we just say? We don't want to lose track of this. Carbon. Okay, so this is one thing that ends up really implied in a lot of these drawings, and it's very easy to lose track of. At all of these little corners, same thing in our line drawing, at all those little corner crosshatches, these are all carbons. This is sort of like the lazy chemist. Okay, so even though it looks like there's nothing there, okay, it's a carbon. So these bonds that we've been doing, these handholds, are carbon to oxygen to carbon. Okay, this was a carbon to a hydroxyl. Okay, most of the stuff we'll look at has a ton of carbons in it, right? We're carbon-based organisms. So carbon is going to serve as the backbone for all of our molecules, and then we're just going to stick interesting side pieces on them that are going to do most of the work. Oops, missed one. So great lead-in. Okay, any questions about that? Okay, so we don't want to lose our carbons. So if you haven't taken chemistry in a long time or ever, right, it's very easy to forget or not know. We good online? All right, let's make our sugars bigger. Oh, just kidding. Don't forget too that we can go the other way. So we did dehydration synthesis to make a bigger one, and we can still do hydrolysis to break it down. So remember with hydrolysis that we're adding that water back in, right? We're creating, let me draw, a bloody stump. There's Jane and Carl again. Right, so I'm going to give Carl the bloody stump this time. Okay, so Jane is going to keep her fist. So she's going to take, remember I have H, H, and O to work with. She's going to take one of those H's. I'm going to add that on. Carl's got a bloody stump, right? Remember, breakups are always harder on somebody. Poor Carl this time is having a rougher go. Can't leave him with a bloody stump. Okay, so on his carbon, we need to put the whole leftover hydroxyl on there. So when they're done, they both have hydroxyls sticking off. So they can go about living their best independent lives, at least until we see them again, right? So this is hydrolysis to lyse or break with water. And hopefully this stuff is starting to feel pretty familiar. And again, if this feels very frustrating, that's okay. Remember, we have that practice worksheet on eLearn. I highly recommend you pull that out and sort of work with it. And you can break up and make up Carl and Jane as many times as you feel. And remember, there's a thruple in there, and so you can make a polysaccharide, make it really big and small as many times to practice dehydration synthesis and hydrolysis. You can also use it to get help with the TAs, or we can MS Teams and work through it as well. Right. So you can really feel good with how these hydroxyl groups are acting. Okay. Any questions about what we're doing up here? Okay. Any questions online before I move forward?
Angela was asking what you were saying about the carbons in each molecule, and I think he was just referring to like the ring structure, like how it's done.
So if I'm interpreting the question correctly, As far as having carbons, all I mean to say is at these intersection points, you see how they're just shown as like bends or crosshairs? Okay, these are all, there's actually something here, even though the drawings are rather lazy. I didn't draw them. This is how all chemists tend to draw these things. And so we want to remember there's actually carbons here. It's very easy to forget about that. Is that your question? Or does that answer your question? They should be able to turn their mics on too. That does? Okay. Good. Okay, anything else before we move on?
Carl has a bloody stump. So the O and H don't belong to him and go to Jane on the glucose molecule. Like the H and O pass to her.
Jane and Carl, so we've given Carl the bloody stump. Okay, so in that case, right, Jane already has the oxygen, so the only thing she's going to get is one hydrogen, right, to tack on to the oxygen she already has, and that's going to give her a whole hydroxyl already. Does that make sense? Okay, so then Carl, because he has a bloody stump, he's going to, let's use a different color. Carl needs the whole leftover hydroxyl from the water, and that's going to attach on to his bloody stump, which is going to give him a whole hydroxyl group. Is that better?
Yeah.
And that's how one water can give us two hydroxyl groups, because we have that one leftover oxygen sort of doing duty. Good questions. Okay, any others? You get everybody online now? Okay, we feel good? All right. Let's look at polysaccharides then. Okay, so if we wanted to make a polysaccharide, we would just do dehydration synthesis more than once, right? We would have taken our, pardon me, disaccharide and added another or another or another on top of that. And remember, as biologists, we're lazy counters. So we have 1, 2, any. Okay? Now, many most of the time can mean 3, but it often means more than that, right? So this often means hundreds or thousands of sugars in the link, okay? So, for example, here, okay, we can see that we still have glucose as our base, right? This was our most simple sugar, but we have thousands of repeating units of it. Okay? And by linking thousands of repeating units of it, we've created cellulose. Okay? And so cellulose is that, pardon me, is that structural unit that I mentioned at the beginning of carbohydrates that works for plants, right? That helps your grass blades stand up, right? That helps your flowers stand up. And so this is a lot of the tough tissue-y stuff inside your plants. And it is pretty tough if you imagine a lot of our mammals, for example, that eat plants. Most of them don't just eat it and move on with their lives, right? If you imagine a goat or a cow, these are base grass-eating animals, and they've got more than one stomach. They have to spit the cud back up and swallow it again. This is some tough material that takes quite a bit to be able to digest properly and actually get anything out of it. Now, in addition to that, we can modify our polysaccharides. In other words, you can add other components or mix other biomolecules in with our carbohydrates and really ramp up what we're doing with them. So for example, chitin is that tough, crunchy material on the exoskeleton of insects. So when you step on a beetle and it makes a crunching noise, or the fact that like beetles can leap off of buildings and not die, okay? That's because of chitin. Okay, it's basically insect armor. Okay, and that's partly because you have polysaccharides mixing in with other minerals and components that make them so tough. In addition, and things that we'll actually be able to see to some degree in this class or in your other bio classes if you're a bio major, we have glycoproteins, okay, and glycolipids. So we can see glyco is, you can almost see the word glucose right in there, right? So we can see that that's a sugar, and we've mixed that with a protein to make a base of our immune system, or we're going to mix that with lipids, right, fats, to make the basket that works with our blood system. Okay, so by mixing these with other biomolecules that we're going to talk about, you can make the core specialized cell systems that function together in our bodies. Okay, I think that finishes up. Does carbohydrates. So any questions about the carb stuff that we've talked about up to this point? Awesome. So here's what I want you to do. Either get out a piece of paper separate from the notes you're taking, or open up a brand new Microsoft Word document. Okay. At the top, you're going to say in class activity number 1. And then you're going to label the first section carbs. This is not COVID friendly. Under the first bullet point, or under carbs, you're going to have 2 bullet points. Okay, your first bullet point is to tell me one thing that carbs are used for. Okay, so why are cells taking that in, or why is the tissue taking that in? What's the point in a carb? Okay, your second bullet point is one feature that you will use to tell the difference between a carb and other biomolecules. Okay, use your terms the best you can. Okay, and try your best to fill this out without looking at your notes first, and then check yourself. Okay, remember, do your best to do this thoroughly. Are you doing this to build your own study guide? Right? You're also going to turn it in, right, for points. So there's that too. Whatever motivates you. Okay, but the only reason you're turning it in for points is because we want you to be making a thorough and useful study guide. the next 20 seconds or so to finish up. Okay, with your sheet, it's really important that you keep track of this because we're going to continue to add to this activity throughout our unit. So if you've done it on a piece of paper, make sure that it's separate from the rest of the notes that you're taking, but it gets tucked in safe and sound. This is now your bebe, right? If you've done it on a Microsoft Word document, okay, make sure that you save the file with a very obvious file name and that it's saved either to your notes folder or to your desktop, again, in a place that you're going to be able to easily find and, and retrieve it. Okay? You'll probably need to recall this note sheet every single time that we're in class until you go to turn it in. In both cases, you're going to turn it in online. The Dropbox will become very obvious. I'll open it up here as soon as we're done. And there's a special tab or week where all of our in-class activities will be turned in. If you've done this on a sheet, all you're going to do is take a photo that is super clear for me, and then you'll paste that photo into a Word document and upload that. And it all works the same way. We've done this before. It's shiny and easy, and we're happy as long as you check what you're turning in and everything's very easy and clear for me. Okay? Shiny? Onwards and upwards then. So let's look at our second biomolecule. So now we have the advantage as we move forward when we're thinking about what is the point of this biomolecule and what are the features of this biomolecule to be able to compare this back to carbs, right? And say, okay, what features can I use to recognize a lipid, and what makes this different from a carbohydrate, right? So we have that advantage. We didn't have that advantage with a carb, right? So you don't have anything to compare it back to. So keep these things in mind as we're moving forward. All right, for the love of lipids. This is also one of our biomolecules that are near and dear to our heart. Okay. These also have quite a few tasks, some of which may surprise you. Okay. Largely for energy, and we generally think of lipids as food, right? Fats and oils. Yes. Okay. There are some structure, and they're going to have some interesting side jobs as well. Okay. So I have a common gracious, lipid. I couldn't come up with the word, and it's on the screen for me. I have a common lipid. Let's not use black. It's going to blend in. Up on the screen for you. Okay, and so we can immediately start to see some of the differences. Okay, the first of which is we don't have any of those hydroxyl groups. So you can really see how important those hydroxyl groups are to a carbohydrate. Right? How iconic those were. And they're entirely lacking here. So what's really key here is what we have a lot of are hydrocarbons. Okay? So we've gone to the effort here to really draw in all those carbons where we were real lazy with that before, right? So a hydrocarbon is more or less what it sounds like. Lots of carbons and lots of hydrogens. Okay? It's long, in most cases longer than what we were looking at with our carbohydrates, although not necessarily exclusively. But it is repetitive and boring, right? Carbon, 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 carbon. Hydrogen, 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 hydrogen. That word is harder to say. Hydrogen, 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 hydrogen. All the way down, and that's all it is. It is a desert of carbon and hydrogen. Okay? The key here is without those hydroxyls, okay, and specifically without that selfish roommate, okay, so without that oxygen, we are now non-polar. Okay, this is also intuitive to us, right? If you take some olive oil and dump it in water, what happens? It divides, it doesn't mix. It sits on top, right? Okay? You can put it in a cup, shake it up really hard. Okay? It may float down through, but it's going to come right back to the top. Okay? Lipids do not play well with water. Okay? And this is because there's no oxygen in there, so they're not going to mix. Okay, we are called hydro for the water, but phobic, as in fearing. We're water fearing. Okay, this works. We can picture this. That's fine. Okay, olive oil versus sugar cubes. I can get on this team. Okay, so let's change colors. The other feature that is iconic and also easy to see is this carboxyl group. And we need to really be careful with our terms now, because this suddenly sounds painfully familiar. So carboxyl, we have that C double bonded O, and a hydroxyl. All right, so that's where it gets its name. Carbon, right? Carbon, and then oxyl, hydroxyl, carboxyl. Okay? But we just had something like this, didn't we? Okay? This business was in our carb. Looks super similar. In fact, the only thing it's missing is that hydroxyl group. Its name is ridiculously similar. What was this called? This is terrible, right? All these freaking names that sound so similar. We're super close. Carbonyl. Carbonyl. Okay, so we still have that carb bit. And then I don't have a mnemonic for this. I was nailing it up to this point. I've never come up with one. So just, okay, it goes with the H. I got nothing, okay? Some of this you just have to work with. So you really have to be careful. All right, so the carbonyl is in the carbohydrates, and the carboxyl is in the lipid. And that carboxyl group is just about the only oxygen that you're going to find. And it's not enough to do anything, right? If we look at the book size of that lipid, having 1 to 2 oxygens, not going to make it play well with others. Okay? Not the friendly kid on the playground. Delicious, but not friendly. We're going to have quite a few of these groups, so practice with them. I almost recommend making like a little chart in your notes to work with the names. I'm going to keep poking you about them as well, like I did here, but it is so unfortunate and easy. Okay? You can hate on some chemists from like the 1700s for this one, but nevertheless, we're stuck with the names as they are. So repetition is going to be your best tool and defense against this. All right, any questions about this? This is where we ended up stopping with the last class because we had some tech issues. So let's go ahead and stop here too. That way everyone's on the same page. Give Fallon a hot second to get the Socrative up. When she does, we'll have the teacher's question, which will be the slide we're on. And we are all set. Okay. And don't forget when you fill that out, right, that your name should go last name, comma, first name, so that your attendance will be very easy and you get counted. Oh, yes, please.